Okay, Chemistry 3101. We're going to start today's lecture off by looking at a couple of practice problems. And I thought we would start with question 14.10. This comes straight out of your textbook. It's one of the questions that I assigned, but I think it's a good place for us to start the day. And all the question is asking is to look at each one of the spectra that are provided and determine whether the spectrum is consistent with the structure of a ketone, an alcohol, a carboxylic acid, a primary amine, or a secondary amine. Yes, in this class, we look at other functional groups. We look at alkenes and alkynes and amides and nitriles and all kinds of other functional groups. But just we're going to choose from this bank of 5 functional groups, if you will. So let's get started with A. And if we start here with A, we see that we have wave number on our x-axis, and then we have percent transmittance over here. Okay, and the first thing that I like to do is maybe draw a line at around 1500, because anything above 1500 is considered the diagnostic region, right? And anything below 1500, this is called the fingerprint region. We don't spend a ton of time in the fingerprint region in this class. However, we do look at it from time to time, so we're not going to completely ignore it. Anyhow, so we've got the diagnostic region and the fingerprint region. And when we look at the diagnostic region, the first thing that stands out to me here is that I have the biggest absorbance at around, so if this is 1500, 1600, 1700, so you have a big absorbance here. It looks to be, it's pretty close to 1700. We could say it's, maybe between 16 and 17. Anyhow, I think it's probably closer to 17 now. Yeah, it's definitely closer to 17 now that I look at it, because this is 17. Oops, that's not what I wanted. This is 17 here. So yeah, it's around 1700. So if I have an absorbance that's at 1700, could anybody tell me what I might be looking at here? What kind of stretch would I be looking at if I have an absorbance around 1700? Does anybody have an idea what kind of stretch this would be if I have an absorbance at 1700 based on the list of IR absorbances that are on the table that I provided for you last class? It's also posted to Canvas. Yeah. So you're in the, yeah, absolutely. So you're all in the right vein. Okay. I see somebody wrote ketone. I see somebody else wrote a carbon-oxygen bond. Somebody else wrote ketone. Okay. So what you got to be careful with is that in a ketone, so if I have a ketone, let me just use a black pen here. If I have a ketone, I have a carbon with a double bond to oxygen. If I have an aldehyde, I have a carbon with a double bond to oxygen. If I have an ester, I have a carbon with a double bond to oxygen. The carbon that is doubly bound to oxygen, that's called a carbonyl. Okay, it's called a carbonyl. And yeah, you're right that the only choice that we have here is a ketone. Actually, a carboxylic acid also has a carbonyl in it. But you might want to just say, okay, well, I know it's a carbonyl, right? It's a carbonyl stretch, okay? And you're right. You're absolutely right that it is a ketone. It's the only possibility here. But I just want you to be aware that it is a carbonyl, all right? So there we go. So we have a carbonyl. And then we could also draw a line, and this is a suggestion by David Klein. We draw a line around 3000, and we see that there's nothing really of interest up here, okay? There's no signals here. So that negates, it can't be an alcohol, so it's not an alcohol, so we'll draw alcohol, cross that out. It's not a carboxylic acid, right? We'd see something much bigger if it was a carboxylic acid. And it's not an amine, okay? So we'll just write amines, and we'll cross those out. And so the only possibility out of all these is what you are all saying, is that this is a ketone, right? We have a ketone, if we're choosing from that bank of possibilities. Well, let's move down to the next one. Let's move down to B. I'm just going to throw this out there to my students, and I'll just ask you without me even doing anything to this one. Do you have any ideas about what kind of functional group would be represented in B? Yeah, you're absolutely right. Good old carboxylic acid. Absolutely, right? When we have an absorbance that is this, this broad, there's nothing that's going to be that broad that we would ever see, in an infrared spectrum. So whenever you see a signal that stretches all the way from, you know, in our book it says it goes from 2,200 reciprocal centimeters to around 3,600, you know, give or take a little bit. But this is an oxygen-hydrogen stretch, okay, from a carboxylic acid. So I'll just write the condensed formula. So we know that we have a carboxylic acid. Is there anything else in the diagnostic region of this spectrum that, you know, represents a part of a carboxylic acid? Anything else in here? What else could mean? Yeah, absolutely. Yeah, 1700 region is what somebody wrote. Yeah. And if you look at the list of frequencies, you go right to the table that I gave you, and you look at carboxylic acid. The first thing it says is the broad oxygen-hydrogen stretching, and then it says at 1710 carbonyl stretching. Okay, so right here at 1710, so this is going to be the carbonyl stretch, right? Because we know that a carboxylic acid possesses an oxygen-hydrogen bond, okay? That's what's shown right here, and it possesses this carbonyl, which is over here. There's also another bond of interest in there. If you look at the carboxylic acid, it also says between 1320 and 1210, you have carbon-oxygen stretching, right? From this bond. And if we look here, if we have 1,000, then we have 1,100, 1,200, probably this signal here is a result of the carbon-oxygen stretch from the single bond, okay? Give me a thumbs up if that clears up a little bit about functional groups and how we see the absorbances in the infrared spectrum. You know, you can not only just say, okay, I have the broad stretch from a carboxylic acid, but I also have the carbonyl, and I have the single carbon-oxygen bond. Well, that's just great. Excellent. Let's move on to C, and let's see what we can see in C, okay? Well, we could do the same thing, and I mean, everybody's got probably a little bit different way of doing these, but we could start by drawing a line at 1500. Okay, we draw our line here, and we'll go into the diagnostic spectrum. I mean, my eyes are drawn to this immediately, right? If you draw a line at 3000, okay, you can see that there's something here, right? If we go back to the ketone spectrum, we said there's nothing there, right? There's nothing of interest there. But in this spectrum, there definitely is something here. Now, it would have to be, you know, somebody who's been looking at the notes and maybe doing a little bit of studying already. But does anybody have an idea about what kind of absorbance this is here? What are we seeing here? So, yeah, it might be a knee-jerk reaction to think it's an alcohol, because with an alcohol, we see a broad stretch, a broad oxygen-hydrogen signal, you know, from 3,200 to 3,600. But this is not big enough, because remember that the oxygen-hydrogen bond has a really strong dipole. And so it also gives you a strong signal. So it's strong and broad, okay? Now, you can obviously see that this is broadened. That's why a lot of you guessed oxygen-hydrogen, right? It is a broad signal. There's no doubt about that. But here's the answer, okay, is that we only have one peak, okay, so to speak. There's only one peak here like that, okay? Now, where does that peak come out? It's around, well, it's around the 3,400 neighborhood, right? If you look at an amine on our table, it says 3250 to 3550. So we have 31, 32. So this one looks like it's maybe around 3250. Either way, it's between 32 to 3,300 reciprocal centimeters. Let's just call it 3250 for fun, okay? And you see that it is broad, but it's not strong, okay? So that indicates that there's some kind of hydrogen bonding, okay? But it is not as, the dipole is not as strong. And so, as Lauren said, it looks like it's not a primary amine, it would be a secondary amine, okay? Because a primary amine has two nitrogen-hydrogen bonds, okay? It's got one here and it's got one here. So a primary amine is always going to give you two peaks. So it's going to give you something like this, like two peaks. Whereas a secondary amine has two R groups and only one nitrogen-hydrogen bond. And so it's going to give you just the one peak like that, Okay, so this means that this is a primary amine. All right. Anyhow, now what are the other options? Alcohol, it's not an alcohol. It's not, the dipole isn't strong enough. The signal isn't strong enough. It's not a ketone, right? We have no carbonyl. Okay, so no carbonyl. Therefore, it's not a carboxylic acid. Okay, it's not a ketone. And so therefore, this one must be a primary amine. Or sorry, a secondary amine. Did I say? Sorry, you guys, I'm getting mixed up with my words. There we go. So yes, it's a secondary amine. Secondary. All right, here we go. All right, let's move on to D. And based off of what I just told you, I'll give you a second to think about this one and see if you can come up with an answer. I'm going to draw some lines to denote the diagnostic region and the fingerprint region. Does anybody have a thought about this one? What functional group might be represented by D? Yeah, Byron says it's oh boy, I got a couple of students that are saying it's a primary amine, and you're absolutely correct. Okay, you see here we have a signal, and I already went through this one and looked at it pretty closely. This one looks to me like it's around 3350, and this one looks like it's around 3450, something like that. So let's just say in the 3350 to 3450 reciprocal centimeter range, and we have these two peaks here. They're broadened because of hydrogen bonding, but the signals aren't as strong as an oxygen-hydrogen signal is, right? Because the dipole isn't as strong, okay? And we talked about how the dipole acts as an antenna, so to speak, for the infrared light, okay? And how it produces a stronger signal. That's something that we looked at during the last lecture. So this will be a primary amine. So there we go. So primary amine. You know, other clues. I mean, and we could sit here all day and analyze this, but we don't have a carbonyl. Okay, we don't have a carbonyl stretch. It's definitely not a carboxylic acid, and it is not a it's not an alcohol. Well, let's move on to the next one. I think the next one might be is kind of interesting here in E. So I'll just throw this out there to my students again while I'm drawing some lines here for the diagnostic region. And I draw a line at 30. Does anybody have an idea about this one? I'm open to my students' suggestions. What functional group might we be seeing in E based off of the choices that we have? Yeah, you nailed it, right? So Byron just said, he just threw it out there. He just says, it's a ketone, Mr. Dion, right? Lauren says the same thing, and you're both 100% correct, okay? So let's go a little faster. You guys know that this is a ketone right away, okay? Based off of what we have to choose. You see that there's nothing of interest up here, okay? So no signal or no absorbance is maybe what I should write, but I'll just call it a signal because it's quicker to write than absorbance. So no absorbance above 3100, so it's not an alcohol, it's not a carboxylic acid, it's not a primary amine, it's not a secondary amine. We don't have a whole lot left over, do we? But what else do we see? We have a really strong signal here, right? Very strong signal, which is a carbonyl stretch, okay? And you see that it's, with this is 16, 17. It looks like it's around, you know, maybe 1710 or something like that. You can see it's, we'll say a little bit greater than 1700 reciprocal centimeters. And so that tells us that out of all of our choices, the only possibility is that this is a ketone. Also notice that a carbonyl has a strong dipole, right? Oxygen is the second most electronegative element on the periodic table, right? So it's got a strong dipole, and that's why a carbonyl produces such a strong absorbance, okay? That's why it's such such a strong signal. All right, and the last one from this section is F, okay? Again, I'll throw this out there to my students who can probably solve it faster than me. Who's got an idea about F? I'm sure some people have ideas about F. So yeah, it's an alcohol. This one is definitely an alcohol. So we have oxygen hydrogen stretch, right? And it's in the 3200 to 3600 reciprocal centimeter range. And so this must be an alcohol, okay? If you look at our table where it says alcohol, it says you can also look for the carbon oxygen stretching between 1250 and 1000. So if this is 1000 Then we have 1250. You see we have a signal here. That must be the carbon-oxygen stretch, all right, from our alcohol, right? Because if you look at an alcohol, right, let's say we have an alcohol like this, right? You have the oxygen-hydrogen stretch, and you also have the carbon-oxygen stretch, okay? So you have to take a look at both of those. Somebody asked a question about what is causing the signal in the 3000 to 2800 range. If you look at all of these spectra, you have a signal here in the 3000 to 2800, right? You have, well, it's buried in the carboxylic acid, but you can see it here. You can see quite a few signals here and quite a few signals here. These are the result of sp3 hybridized carbon-hydrogen bonds, okay? And they're ubiquitous in organic chemistry. We're going to see them in almost every spectrum. So that's why we always see them. This is a sp3 hybridized carbon-hydrogen stretch, okay? You do not have to annotate those. So I'm going to give you problems where I'll say, you know, annotate this spectrum or something, especially if you're in the lab. We'll do that a lot. You don't have to annotate these because there's sp3 hybridized carbon-hydrogen stretches in, you know, probably most of the compounds that we're going to look at. Not all, definitely not all. Like, let's say we looked at a compound, let's say we looked at the infrared spectrum of a compound like this is called aniline, okay? This is the name of this compound. There's no sp3 hybridized carbon-hydrogen stretch, so you wouldn't really see a signal there, okay? All right, anyhow, hopefully that answers that question. Let's try to do 14.12 a little quicker. It might be hard for you to see all the choices on the screen here. Let's see if we can solve this one kind of quickly. It says here, match each compound with the appropriate infrared spectrum. Look, here's what we've got. We've got an alkane. This is pentane, okay? Then we've got an alkene here, okay? This is called 1-pentene. Here we have an alcohol. This is a carboxylic acid, so carboxylic acid. This is actually called malonic acid. If you studied biology, you might have heard of that. Here we have a primary amine, and here we have an ester. Now I know some of you might have the textbook in front of you on another screen, but I'm just going to put the first 4 spectra up here. Is there anything, you know, out of A, B, C, and D, and yes, there are more down here, but out of these 4, is there anything that, you know, any one of these spectra that a student's like, I know what the answer is, I know which compound, you know, just by looking at these super quickly? Any of these? A, B, C, or D? Okay, I see somebody says a ketone for B. Is there any, and I think you're in the right, I think you're right, Lauren, okay? But I want to address what Byron's saying. He's saying D. What are you saying about D, Byron? What do you think might be in D? Yeah, absolutely. Advita's got it. It's an alcohol, right? If we look at all of these, it's the only one with that broad stretch in the 3200 to 3600 range. So this is the oxygen-hydrogen stretch, okay? And you can see that there's probably the carbon-oxygen stretch is here as well. And so this is the alcohol. So we eliminated that one. Boom, just like that. I'll go back to what Lauren said. She said a ketone in B. If you look at B, she said, look, there's nothing above 3000, okay? So it's not an alcohol. It's not a carboxylic acid. It's not a primary amine, all right? Now, there is no ketone on here, all right? But there is a compound with a carbonyl, right? And that compound is an ester. So this would be our carbonyl stretch, okay? And if you look at the signal, the carbonyl stretch for an ester, okay, go on your table and you look at ester. The carbonyl stretch is around 1735, which is consistent with what we see here. You also see that an ester has a carbon-oxygen stretch between 1000 and 1300, and that would be this one here. This is your CO stretch, and this is your ester, okay? All right, I'm going to go to the next ones, okay, because I bet you there's one of these that everybody notices right away. About E and F, is there anything that you could pick out here quickly, really quickly? Heck yeah, yeah. It's not what I was expecting. Okay. My students are saying a primary amine, and they're correct. Yeah, you see you have the 2 signals here for a primary amine. So this is our primary amine. right? You can see they're broadened. Okay, so these are the nitrogen-hydrogen stretches, okay? Nitrogen-hydrogen stretch. I mean, if you just want to write NH stretch, that's totally fine with me. Okay, Moira, that's where I was thinking my students would go. I was thinking that everybody would just go to E and just be like, well, come on, Mr. Dion. I mean, look at the size of this thing. It goes all the way from here to all the way down here, right? This is the oxygen-hydrogen stretch, okay, from, not form, from a carboxylic acid. So this is carboxylic acid. You also have the carbonyl stretch here, okay, carbonyl stretch of the carboxylic acid. Well, what have we eliminated? We eliminated the primary amine, the ester, the carboxylic acid. So what do we got left? We got an alkene and an alkane. And one must be A and one must be C. Does anybody have an idea which one might be the alkene? Anybody have an idea which one might be the alkene? Yeah, absolutely. Jay, Byron, you're absolutely correct. Jessica, Kayla, hey, it's the alkene, right? This is an alkene. Let me write it here. I'll just put alkene, and let me get a better colored pen here than green. Where are we? Here we go. Now, how did you know it was an alkene? If we draw a line at 1500, okay? Now, a carbon-carbon stretch, okay, a double bond stretch. If you look at alkene on your sheet, it says it's around 1630. Look, we've got 15, 16. It's right in that neighborhood of 15 to 1600. So it's this one here. It's not strong, right? It's not a strong signal. It can't be, right? Because there's no strong dipole in a carbon-carbon double bond, right? If this was symmetrical, there would be no dipole, but there's a little bit of a dipole here. What else? We know that we have sp2 hybridized carbon-hydrogen stretches. And if you draw a line, and I'm going to try not to bury it here, at 3000, you can see this signal here, which is around 3100 reciprocal centimeters. That's going to be our sp2 hybridized carbon-hydrogen stretch. Okay, there we go. And then in C, we don't really see anything of interest here, do we? We have no absorbance here. We don't have anything in here. And as one of my students asked me, they said, well, what's this here, right? All these is nothing more than sp3 hybridized carbon-hydrogen stretches. Now, again, normally, you know, for most of you who are taking the lab class with me, I would never ask you to annotate that, to write anything out, because it's so common. But just because it's the only possibility left, we'll write it there, and we'll say that this is our alkane. Okay, that's our alkane. Who's feeling a little bit better about infrared spectroscopy after looking at some examples this morning? Is anybody feeling say, hey, I've improved my quality of understanding by, I don't know, 10, 15, 20%? Because that would be a really good thing. All right, awesome. That's fantastic. I'm really happy to see that. Okay. Again, on Friday, if we have more time, we're going to take a look at some more examples. If you're the kind of person that likes to peruse the internet and look for, you know, extra practice problems or something, I always have a few people that are really keen. You could do that, but let me just throw something out there to you, because a lot of you are taking Chemistry 3102 right now, and I don't like to marry the two or wed the two classes a whole lot because they are separate classes. But if you're in Chemistry 3102, you would have a copy of the Schafstall textbook, right? You would have bought a copy of that Schafstall textbook. Well, let me tell you that infrared spectroscopy is technique, so technique M, okay, in the textbook. And in the Schafstall textbook, he goes into quite a bit more detail than our textbook does, than the Klein textbook does. So if you need more information, if you're like, I'm kind of not 100% sure on one of the concepts, I guarantee you that if you read that, which it's not a long read, the technique is not a long read, it's a few pages, that will help clear up, and it'll also open your eyes to how much more there is to learn about infrared spectroscopy. And also, I'll just throw this out there to you. If you are in the lab class, when it comes time to look at infrared spectroscopy, because we will be studying that in the lab, all these concepts that we've studied so far in 3101, I'm not going to go over them because I'm not going to, you know, preach the same thing twice, okay? However, in that class, we will look at a couple of functional groups that aren't really covered in this class. So we're going to actually add to it. And like, let me give you an example of something that I don't think is covered in the Klein textbook, and that would be something like an anhydride. So this is a functional group called an anhydride, and the carbonyl stretches for a anhydride come out at 1760 and 1810 reciprocal centimeters. Okay, so something that's not even in the table in our book. It's not in the table that I gave you. The material that's presented in Klein, you need that for the quizzes in this class, okay? So you don't have to go read another class's textbook to master the material that you need to know for this class, okay? All right, well, it's almost 8:30. I think it's time for us to switch gears and take a look at mass spectrometry. I'm just gonna find my place here. And hopefully you all saw my announcement that I posted. It was a little bit late last evening, but I posted an announcement that I had made a couple of videos that covered the content from sections 14.8. So I had from 14.8 to 14.11. So I covered those sections in some videos. It will not take you a long time, or if you've watched those already, you probably know. Figured out it's not long. It's about 17 minutes worth of videos just to cover those 3 sections. So based on that, I'm going to go over these 3 sections in class right now, but I'm going to try to go over them a little quicker. I have a hard time doing that. I like to talk a lot about chemistry because I always get excited and want to say lots of things, but I'll do my best to keep it succinct so we can really get into studying, how do we solve problems in mass spectrometry? Because hopefully something that you've really figured out in the first section of chapter 14 is what? Is that when you saw me lecture, listen to me lecture about the theory of IR, I'm sure you all understood it. We're like, yeah, that's interesting, Mr. Dion, that's cool, yeah. But it doesn't really crystallize in your mind. It's hard to really understand the theory until you put it into practice. You know what I mean? That's why I see students saying, oh, I understand it a lot better now, right? Byron says, I understand it a lot better. Because you're going to see the same thing with mass spectrometry. Once we practice it, it'll become abundantly clear, as to what the heck is going on, okay? So 2 different words, spectroscopy, spectrometry, right? Spectroscopy is the interaction between electromagnetic radiation, so light, and matter. Spectrometry is the interaction between energy and matter. So we're not talking about shining light or anything like that. We're just subjecting the matter to an energy source is the way what I'm trying to say. Anyhow, in infrared spectroscopy, what were we trying to do? We were trying to determine functional groups in an organic compound. What the heck is mass spectrometry used for, Mr. Dion? Well, glad you asked. Mass spectrometry is used to determine molar mass and the formula of a compound. Say, for example, you're looking at 2 different drugs. Let's say you were looking at, say, I don't know, say you're looking at cocaine versus salicylic acid, right? 2 very different drugs, and they're going to have different molar masses. So you could use mass spectrometry to differentiate between the 2, but we can do a lot more than that. That's a very simple example. So the way that we do mass spectrometry is we use an instrument called a mass spectrometer. Some of them can be really, really expensive machines. And what you do with a mass spectrometer is that you vaporize a compound, then it becomes ionized. So you remember what ions are, right? Like carbocations, anions. Anyhow, we're going to look at ions. And then it undergoes fragmentation. What's fragmentation? Fragmentation is nothing more than breaking apart. Okay? Now you might be wondering, hey, Mr. Dion, what if I have a solid organic compound, right? Something that doesn't melt until, 150 degrees Celsius. How are you going to vaporize it? How are you going to convert it to a gas? Well, the way that that's done in the mass spectrometer is by subjecting the compound, obviously, to high temperature, right? Because then it's going to, convert it from a solid to a liquid and then to a gas to vaporize it, but also low pressure, right? Because you know that boiling point decreases as you lower pressure. So it's usually a vacuum with a really high temperature. Anyhow, then what we do is we produce ions and we detect those ions and we graph them out based on their masses. So we start on the low end of low masses and then we graph all the way up to high masses. Now notice what it says here, and this is something that's really important for you, is that masses of ions are detected. The only masses that you see in a mass spectrum, look deep into my eyes, I'm going to hypnotize you, okay? The only masses that you see are ions. If something doesn't have a charge, you don't see it in the mass spectrum, okay? The only thing you're ever going to see is something that's an ion. And we're going to see two types of ions that we're concerned with in this class. We're going to look at cations, and I know that everybody knows what a cation is. And we're also going to see something that are called radical cations. So radical cations. Okay, so cations and radical cations are the only things that we're going to see in our mass spectrum. So there are several different types of mass spectrometry. The most common method that we use for ionizing molecules is called electron impact ionization. We shorten that to EI. And basically what you do is you take your organic molecule. This is just some generic molecule here. It kind of looks like 2,2,3,3 tetramethyl butane, but whatever. Anyhow, we take that and we bombard it with a high energy beam of electrons. So poof, you just hit it with electrons, okay? Really high energy. The beam of electrons hits it so hard that it actually knocks out an electron. Now, you know that in a sigma bond, right? This is a sigma bond right here. You know that in a covalent sigma bond that there are two electrons in that bond, right? Two electrons that are shared between these two carbon atoms. So what's going to happen is when it gets hit by that beam of electrons, you lose an electron. So this is one of the unpaired electrons. Now, we haven't done chapter 10 yet in this book, okay? But when in chapter 10 deals with the subject of radicals, okay? But what you need to know is that a radical is an unpaired electron. And you would have seen that concept even in general chemistry. I've taught general chemistry long enough to know that we bring up the subject of unpaired electrons in Lewis structures. So an unpaired electron is a radical. So think about it. If you lose an electron, what happens? You become positive. So we end up with something that's a cation and it's a radical. So both, okay? And then you lose an electron. Now, again, all we're going to see in the spectrum is going to be something that's charged, okay? So we call that a molecular ion, and we'll get into that in a second. Now, what about the mass of that electron? There might be somebody who's saying, well, come on, Mr. Dien, you're losing an electron, so what's going on there? Well, the mass of the radical cation is going to be the same as the parent compound, right? This is what we call the parent, right? This is where the radical cation came from. The mass of an electron is so small compared to the compound that it is essentially negligible. And so the mass here is going to be the same as the mass here, okay? So those are going to be equal to each other. Now, that radical cation, so you take the whole compound, the whole molecule, right? We just have an organic molecule. We hit it with a high energy beam of electrons. It loses an electron. It becomes a radical cation. If that radical cation remains intact, and if you're wondering, what do you mean by intact? If it stays, okay, and it doesn't fall apart, we call that a molecular ion or a parent ion. And we use this symbol here. So M plus with this radical up in the top right corner here. Okay, so a molecular ion, or we call it a parent ion. So you take the whole molecule, the whole damn thing, you knock an electron off, you have now a molecular ion or a parent ion. Okay, now what about that molecular ion or that parent ion? Well, it says here that most parent ions can fragment into a radical and a cation. In this case, it's showing a carbocation being formed. Now, I'm not going to ask you to draw any fish hook arrows. This is called a fish hook arrow. Remember the whole, double-headed arrow, which represents the movement of two electrons? When you see an arrow with one barb on it like that, that means the movement of one electron. Again, drawing the curved arrows is something that we'll do in chapter 10, so you don't have to worry about it, okay? But what you have to know is that parent ion can typically break apart, okay? We get a radical here and a carbocation. We are not going to detect the radical in our mass spectrum, are we? However, we are going to detect the carbocation. Why? Because it's got a charge, right? And I said that we only detect ions in our mass spectrum. Why? Because when you take the the fragments that are ionized and you put them through a magnetic field, they're going to be deflected by that magnetic field, okay? Now, all the ions that we're going to look at in this class are always going to have a charge of +1. Okay, so charge is represented by the letter Z. So here's our charge. Okay, so charge is always going to be +1. That doesn't change. Okay, but we plot them by their mass to charge ratio. So if we have our masses being different, the smaller the mass, the greater the ion is going to be deflected by the magnet, and the heavier the ion, the less it's going to be deflected. And that's how we're able to get a spectrum, right? We get a range of masses and we get different peaks in our spectrum. All right, here we go. So here's a mass spectrum of the simplest organic molecule possible, which is methane, right? Everybody should know what methane is by now, CH4. And now it says here, the mass spectrum shows the relative abundance of each cation that was detected. So you see we have all these lines over here, right? We have all these vertical lines. So what the heck are these lines here? Well, before we get into those lines, I want to address something that's not really addressed directly in our textbook. It's one of the few things that I find our textbook, it doesn't really mention it a whole hell of a lot. And that is that there's what is called low resolution mass spectrometry and high resolution mass spectrometry. If you look at our textbook, I have it open right here in front of me. If you look at chapter section 14.13, it deals with, so 14.13, there's a whole section about what's called HRMS. That's high resolution mass spectrometry. We are going to skip that section. It's not covered in our class. You don't even have to worry about reading that section. However, you do, so what we look at in our class in Chemistry 31 is actually low resolution mass spectrometry. Now, in low resolution mass spectrometry, atomic masses are reported to the nearest atomic mass unit. Now, this is something, I didn't even think about this until I started teaching from this textbook a number of years ago. And I introduced the subject to the students and everybody seemed happy. And then we started to look at some practice problems. And students were using masses that they took from the periodic table. Now, I've been studying chemistry for a long time. I wasn't doing that. But I was wondering, like, why are my students doing that? And it was because the book didn't actually address this. So since we're using masses that are rounded to the nearest atomic mass unit, let me show you the masses that you're going to need to know or have memorized for this class, okay? Now, when I say memorized, if you look at the periodic table, you're going to be able to figure them out really quickly. But the mass for a hydrogen to the nearest atomic mass unit is going to be 1, right? It would be 1 AMU. So that's the mass we'll use for a hydrogen. We're not going to use 1.01. We just use 1. For a carbon, it has a mass of 12. We don't use 12.01. We just use 12. For an oxygen, we use 16. For a nitrogen, we use 14. For a chlorine, we use 35. For a bromine, we use 79. For a fluorine, we don't see a lot of fluorine in this class, but we might see from time to time. We use 19. And for iodine, we use 127. So those are the masses that I'm going to use. Again, why? Because we're dealing with low resolution mass spectrometry. So now that we've got that out of the way, let's go back to this beautiful spectrum that we have over here and look at all of these lines in here, okay, or the peaks in our mass spectrum. And there's always, sometimes students have a hard time analyzing what the hell is going on here. You have to be able to use your mind's eye to divide this. You have 15, 16, 17, 18, 19, 20, right? So you see that we have the biggest peak is actually at 16. Now remember, this represents a mass over charge that is equal to 16. Where does that come from? Well, if I calculate CH4, son of a gun. Hey, pretty good. If I calculate CH4, I've got 1 carbon. Where's my pen? 1 carbon, which has a mass of 12, and I've got 4 hydrogens, which each have a mass of 1. So that gives me 12 plus 4, which gives me 16. So what did I do? I hit the methane molecule with a high energy beam of electrons. I knocked 1 electron out. I made my molecular ion. And so this is my molecular ion peak, okay, where I have a mass over charge of 16. So I'm going to label that as my molecular ion peak. This peak here is my molecular ion, which I denote like that. Now you might be wondering, what the hell are all the other peaks in there? You got a whole bunch of stuff in there, Mr. Dion. We'll get to that in a second. But before we do that, I want to address the fact that the molecular ion is the tallest peak because we have a special name for the tallest peak in mass spectrometry. We call it the base peak, right? It's kind of like everything is based off of that. We assign the base peak an abundance, a relative abundance of 100%, and everything else is based off of that. So if you look here, you have, mass over charge that's equal to 15. So if you look at this line right here, right, this is mass over charge is equal to 15, okay? Well, that's one less than our molecular ion, all right? And that is, you know, what is it, around 80% or a little more than 80% abundant, okay? So that's what's going on there. Now let's talk about this fragmentation of the methane molecule a little bit more, because you might be wondering, now where again does that come from, Mr. Dion? That that peak at 15, where the hell is that coming from? Well, if I have my parent ion, my molecular ion, okay, which has a mass over charge of 16, I showed you where that mass comes from. That's a radical cation, right? This is a radical and it's a cation. Well, that can fragment or break apart, right? Because it's not going to be completely stable. If it loses a hydrogen radical, so this is a hydrogen, anyhow, we'll just leave it. So it loses the hydrogen radical, and we end up forming this carbocation, which is going to have a mass over charge of 15, right? We've got 1 carbon plus 3 hydrogens. Each one has a mass of 1. We get 15, okay? And so what's going to happen is that this is going to be unstable, and then it can lose another hydrogen, then it can lose another hydrogen, so on and so forth. And that's why we see signals at, or peaks at 15, 14, 13, and 12, right? Okay. There we go. Well, before we move on, I just want to address one more thing, and that's for my students who are super astute. And if you didn't watch the videos, you probably noticed that there's this peak here at 17. And you might be wondering, what? Why is there a peak at 17? Well, if you were to measure the relative heights of the molecular ion and this peak at 17, you'd see that the peak at 17 is about 1.1% as big as the molecular ion. And there's a good reason for that. This is something that I didn't cover in my videos, but mass spectrometry really has so many uses. I remember when I was doing my chemistry degree, one of my best friends in my class, his father was an organic chemistry professor at a different university. And I remember him telling us, he's like, fellas, if you want to make money, you know, being an organic chemist, mass spectrometry is probably a good place to be. If you're a mass spec expert, there's lots of opportunity out there. Anyhow, you also have to be really good at instrumentation. So you have to be good with working with computers and complex machinery and things like that. So not the kind of place that I would want to be. Anyhow, so it says here, mass spec is very sensitive, organic compounds. So if you work in the pharmaceutical industry, let's say you give a drug to an animal, like a rat or a rhesus monkey or a beagle or something like that, usually the biologist will monitor metabolites and, you know, the drug itself in, you know, blood or urine or feces of the animal. And so they detect it using mass spectrometry. Amino acid sequencing, I worked with a guy who is an expert in that. I'm not really interested in it, but anyhow, it's used in that. What else? Of course, if you're an environmental chemist, okay, we actually have an environmental chemist on staff at UCCS. She's an expert in testing water quality, even the quality of alcoholic beverages, and they use mass spectrometry to detect all kinds of things there. Forensics, you know, I always, as I told you, I don't know, before, I probably always make the joke about these crime shows where they're injecting, you know, samples directly into a spectrometer, which is impossible. But there's a lot of opportunity out there for anybody who finds mass spectrometry interesting. And also, again, and I'll just put another plug in here for the Schafzahl book. If you have the Chemistry 3102 textbook, it's Technique P. And he goes into quite a bit more detail about mass spec in there. Okay, so let's switch gears here and let's talk a little bit more about that molecular ion. Okay, if you look at benzene, okay, benzene, what's the formula of benzene? It's C6H6. So if we tally that up, it's going to be 12 times 6, which equals, you don't need a calculator to multiply 12 times 6. 12 times 6, which is equal to 72. And then you have 6 times 1, which gives you 6. So that gives you a mass overcharge of 78. So if we knock 1 electron off of this, we would get our parent ion. And you can see that we have 75, 76, 77, 78. So this is our molecular ion right here at a mass overcharge equal to 78. What else do you notice about this spectrum? The thing that I notice is that there aren't a whole heck of a lot of fragments, are there? There's not much in there. And the reason why is because benzene is quite a stable molecule. But in this spectrum, our parent ion, or our molecular ion, is actually the base peak, right? It has the abundance of 100%, right? It's the tallest one in here. But what you're going to see is that not every mass spectrum has a molecular ion or a parent ion that is actually the base peak. Let's look at pentane. Okay, this is just plain old pentane, right? It's just a liquid. You're injecting that into the instrument. What's the formula? You have C5H12. So if we have 5 times 12, so we take 5 times 12, we get 60. And then we have 12 times 1, we get 12, and then we get 72. Okay, so our molecular ion is at 72. Let's analyze here. Okay, we have, look, 70, 71, 72. So this is our molecular ion right here at a mass over charge that's equal to 72. It is not the base peak, is it? Right? Not even close. Our base peak is way the heck down here. Okay, our base peak is at 40. Let's see here, 40, 41, 42, 43. So the base peak is actually at a mass over charge equal to 43. Now, if you take 72 and you subtract 43 from it, you end up with 29. You see that there's a difference of 29 mass units from the molecular ion to here, okay? So we could say that this is M plus the molecular ion subtract 29. And there's a good reason for that loss of 29, and I'll explain that in a little bit. Anyhow, so one of the first things you want to do with a mass spec is to identify the molecular ion. Almost all spectra, and I can't think of every single, or I can't remember every example that's in the book off the top of my head, but I think that virtually every example that you're going to see in Chemistry 3101 has the parent ion. You're going to be able to see the parent ion, because there are lots of mass spectra that don't give you a parent ion. All right, but anyhow, we're almost always going to have it. So then what do you do with it? Well, the parent ion tells you the molar mass of the compound. You might be thinking, whoop-de-doo. Okay, great. What the heck does that tell me about anything? Well, there's a really important rule that you have to know called the nitrogen rule, which can give you lots of information about the compound, or some interesting information. It's simply this. If you have an odd massed molecular ion, what that means is that you have an odd number of nitrogens in the molecule. Simple as that. You're like, really? Yeah. So if you, let's say you had a molecule and you had a parent ion that was, your molecular ion, and it had a mass over charge of, let's say, 343. It's an odd number. You can't divide it by 2 and get a whole number. And so that would tell you that you've got an odd number of nitrogens. You've either got 1, 3, 5, 7, 9, so on and so forth. If you have a mass over charge, molecular ion or parent ion that has an even mass, which is most compounds that we're going to look at, you've either got no nitrogen, so absence of nitrogen, which means no nitrogen, or an even number of nitrogens. What's the best way to understand anything in organic chemistry? Look at some examples. Look here. We have no nitrogens in this molecule. It's got an even mass. Look at the next one. We've got 1 nitrogen. It's got an odd mass, and when you have an even number of nitrogens, you go back to having an even mass. So something I'll ask you to do every time you see a spectrum and you have the parent ion, the molecular ion, I'm going to ask you to analyze it in terms of the nitrogen rule. Okay, so again, this is called, I don't even have it written down here. Let's write it down. This is called the nitrogen rule. Okay, you got to know the nitrogen rule in organic chemistry. What other information can we get from our spectrum? Well, let's talk about that M+1 peak that I referred to. I didn't go into detail about it. There's an M+1 here, right? Our molecular ion is right here. This is our parent. It's got a mass over charge that's equal to 16. We went over that, but here we've got something that has a mass of 17. We call that an M+1 peak, right? Because take our molecular ion, you add 1 to it, and you get 17. So this is our M+1 ion. Now, it's around 1%. If you listened carefully to what I said in the lecture this morning, you'd probably notice that I said it was around 1.1% as tall as the base peak. There's a good reason for that, okay? We can round that down to 1%, okay? And the reason why is because there are 2 isotopes of carbon that are going to be abundant, okay? There's 3 isotopes of carbon, but the third one is so so small we can negate it. But we can have either carbon-12, okay, or we can have carbon-13. Carbon-12 makes up about 99% of all carbon atoms, and carbon-13 makes up around 1% of all carbon atoms. So that means that when you put your sample in the spectrometer, right, 1% of all the carbons are going to be carbon-13. Now, since there's only one carbon in the whole dang molecule, right, simplest possible organic molecule, that means it's your M+1 peak, which comes from the carbon-13 isotope, okay? Since only one out of every 100 molecules is going to have carbon-13 in it, that means that your M+1 peak is going to be about 1%, the size of the base peak. Give me a thumbs up if that makes some sense to you. You're like, yeah, I remember carbon-13. And carbon dating, okay, you might have learned about carbon dating in general chemistry. Yeah, and it explains, you know, how we all have a constant amount of carbon-13 in our bodies. You know, where do we get carbon-13? The food that we eat, right? But then carbon-13 isn't a stable isotope, so it starts degrading, and based off of the half-life of carbon-13, you can carbon date, you know, things that are dead, like tissues or human beings or whatever. Anyhow, there we go. Okay. So let's think about this. If we have decane, okay, what's decane? Decane is C10H, come on, Mr. Dion, H22, okay? So decane is 10 carbons in it. Well, let's think about what the height of the M+1 peak would be. Well, there's 10 carbons in there, and every one, you know, there's a 1% chance that it could be carbon-13. So I have 10 carbon atoms, so I multiply that by 1, right? And I get approximately 10%, okay, or thereabouts, okay? So you see that the M+1 peak is around 10% as high as the base peak. Pretty cool, huh? Very neat. And so what the take-home message is, the whole point of section 1410 could be summarized in this sentence right here. If you compare the heights of the M+1 peak to the parent ion, you can estimate how many carbon atoms are in the molecule. Now let me go back to my textbook here. I just want to, because I don't know if I have time to look at it with you right now, but it's Skill Builder 14.3. So yes, right here, I had it on the slide, okay? If you have time, I would like you to take a look at that before Friday, Skill Builder 14.13, because I want to take a look at question 14.20 with you on Friday. Okay, so on Friday, we're going to take a look at this question, and we're going to actually just look at some data and be able to determine the number of carbon atoms in a compound, okay? I want you to take a look at it before class on Friday, especially if you can, please, and we'll take a look at it on Friday. Really interesting. Okay, well, here's something new, an M+2 peak. What the heck's an M+2 peak, Mr. Dion? Well, the only time you're going to see an M+2 peak in this class is in two different situations. It's when you either have chlorine or bromine in your molecule. Just those two halogens, not fluorine, not iodine. Don't worry about those today, okay? But when you have chlorine or bromine in your molecule, you can get an M+2 peak. So that's the molecular ion +2, okay? All right, so if we look at what's going on here in this mass spectrum, this is called chlorobenzene. So chlorobenzene here. Okay, you can see it's obviously got a chlorine in it. Well, chlorine has two isotopes that are the most abundant, chlorine-35 and chlorine-37. They have relative abundances of 76 and 24% respectively. So what's that? A ratio of about 3 to 1. Okay? So what that means is that if you have a compound that has got one chlorine atom in it, it's going to have two peaks, one at the molecular ion, right, the parent, and then you're going to have an M+2 peak, okay? Son of a gun. Anyhow, you get my idea. There we go. Okay. That are going to have a ratio of 3 to 1. Now let's calculate the mass of chlorobenzene. So we've got C6H5Cl. So if we've got 6 times 12, so 12 times 6 gives us Can you guys see my mass spectrum again?
Yeah, we can.
Okay, thanks. Good. Situation averted, or crisis averted. Anyhow, so we're going to tally up the mass of the 6 carbons, okay, that's the 72, plus the 5 hydrogens, plus the chlorine. Now again, chlorine has 2 isotopes, but you always go with the most abundant, which is chlorine 35, okay, so you add 35. So that gives you 72 plus 40, which gives you 112. So the parent should be 112. Let's see here. You've got 110, 111, 112, okay? So here's our molecular ion, okay? It's got a mass over charge that's equal to 112. Look at over here. You got 113, 114. So you've got mass over charge here is equal to 114, and that is your M+2 ion. Look at the relative heights. They're about 3 to 1. Therefore, you know you have chlorine present in the molecule. Okay, simple as that. So you know how you guys get really accustomed to looking at infrared spectra with me, and you'd say, "Oh, Mr. Dion, that's an alcohol. Oh, Mr. Dion, that's a carboxylic acid." You know how you could recognize it really quickly there? Well, what you're going to find is that when you study mass spectrometry, you're going to be able to recognize chlorine, quicker than a cat can blink its eye. Okay, as soon as you see 2 peaks there, you have an M+2 that's got 1/3 the height. You're going to say, Mr. Dion, that's a chlorine. Okay, I know it immediately. Okay, now let's take a look at the bromine, because I told you bromine was important too. I'll try to go a little quicker here. The 2 isotopes of bromine are bromine 79 and bromine 81. 79 is more abundant, not much, but a little bit, at 51%. And so we should get our molecular ion, and we should get an M+2 peak, but they're going to be what? Pretty close to a 1-to-1 ratio. And you see that right here. If you calculate the mass of this molecule, this is bromobenzene. It's got C6H5Br. Okay, so we've got 6 carbons. So we've got 72 plus 5 plus 79. That gives us 156. Now this one's a little dicier, but you gotta be Johnny on the spot here. So we got 151, 151, 152, 153, 154, 155, 156. So this is our mass over charge is equal to 156. This is our parent, and then you can see here that you have 156, 157, 158. Okay, so this is mass over charge is equal to 158. So this is our M+2 peak. Okay, and look at their relative heights. They're almost equal. Therefore, you have bromine. So 1-to-1 ratio. Therefore, bromine is present. Simple as that. What do you think? Give me a thumbs up if you follow me on analyzing the M+2 for a bromine or a chlorine. That's all you need to know for the M+2 rule. You're like, Mr. Dion, that I wish it was all like that. Is anybody with me on that one? Good, thanks. Awesome. Wonderful, wonderful. Okay, it might take me longer to explain all this than I thought. Anyhow, so section 14.12. Look, if you're interested, and I don't blame you if you don't want to look up everything that we learned in the class in detail, but if you look at the Schafstall book, again, this is for my 3102 students. If you look up technique P, okay, which again is mass spec, so technique P, and you look up the section that deals with fragments, you'll see like, whoa, baby, he's got a list of fragments, but from here to I-25, okay, he's got a huge list of fragments. Luckily, in our class, and I'm going to skip ahead here and show you something, okay, the only fragments that you need to know for 3101, so in our quiz, in our final exam, would be the fragments that you're going to see in table 14.3, okay? So don't stress about, oh, I have to learn 1,000 fragments. When I was an undergrad, I took a class only on spectroscopy, and I did have to learn, 100 different fragments. Took forever. Anyhow, so let's talk about those fragments, right? So far, we haven't really talked about them. We talked about the methane, and then how we made the methane radical cation, then how it lost a hydrogen, and you get the carbocation, which had a mass over charge of 15, then it could lose other hydrogens. What if we get a molecule like pentane? Wow, that's a big molecule, okay? You take pentane. I love how he just starts with a radical cation, right? He makes a lot of assumptions. So you start with pentane. You hit it with 1,600 kilocalories per mole of energy, right? That's your beam of electrons. You knock an electron off and you make a radical cation, okay? So you would detect that radical cation in the spectrometer. Okay, if we go back a few slides. Okay, you might remember, where was it? Where's our pentane? Our pentane has a mass overcharge of 72. So let's go back here. Where was it? Right here. So we know that our molecular ion, okay, has a mass of 72. Okay, well, what happens is that since the radical cation is not stable, it can break apart. It can fall apart. Well, how is it going to fall apart? It's going to fall apart by losing radicals. What are the types of radicals I could lose? You could lose a methyl radical. So this is a methyl radical. Radical. Okay. This is an ethyl radical. This is a propyl radical. This is a butyl radical. And when you lose those different radicals, you end up with these different ions over here. Now, again, the reason that the ions are highlighted in green is because that's what we're worried about, right? Because the mass spec only detects charged species. Okay, we're not going to detect any of these radicals, only what's charged. But look at the clues that we can get from these fragments. If we lose 15, that means that we'll have lost a methyl radical, because a methyl weighs 15. Okay, and I showed you that earlier today. If you lose 29, that means that you will have lost an ethyl radical, right? 2 carbons, 24, 25, 26, 27, 28, 29 for each of the hydrogens. If you lose 43, that means you've lost a propyl, 3 carbons, 36, 37, 38, 39, 40, 41, 42, 43. There you go. And if you lose a butyl, then it's going to be a loss of 57. Okay, so you remember how earlier on I said M minus 29? I showed you a difference of 29. Well, now you know the significance. Now you know that that was because based on the loss of an ethyl radical. All right. Now, what if we have a compound that's not as, not like pentane? Okay, if you take a look at this compound here, so this molecular ion would come from what? 2,2-dimethylpentane, right? So you'd start out with this 1, 2, 4, 5, 2,2-dimethylpentane. You subject it to 1,600 kilocalories per mole of energy, and you form a molecular ion. Okay, so there's your parent, or your molecular ion. Now it says here that it's going to end up fragmenting here, so that you're going to end up with a tertiary carbocation and a primary radical. Now, why are they just highlighting that? Well, let's take a look. It says that while all possible fragments can happen, and all of them are observed, right? You can lose just the methyl radical, sure. You could lose this methyl radical, sure. You could lose the ethyl, sure. That can happen. Okay, a lot of stuff can happen. But since a tertiary carbocation is more stable than a primary or secondary, that it makes sense that you would lose the propyl radical, right? This is the propyl radical. Why does it make sense? Because if you lose a propyl radical, you're going to get the most stable carbocation, a tertiary carbocation, like that. All right. Now, just to review, if you're unsure, when it comes to carbocations, a tertiary carbocation is going to be more stable than a secondary carbocation. Okay. And that's going to be more stable than a primary carbocation. And that's going to be more stable than a methyl carbocation. So a methyl is the least stable of all the carbocations. So most stable and least stable. Okay, what about radicals? Now again, we haven't covered the subject of radicals in this class, but they follow a similar trend. Okay, a very similar trend. A tertiary radical is going to be more stable than a secondary radical, which is going to be more stable than a primary radical, and a methyl radical is going to be the least stable of all. Okay, so let's take a break just for a second. Take a deep breath. Done. Okay, so if there's somebody out there who's listening to me, and I bet you that all of you picked this out faster than I can explain it to you. Okay, did anybody notice or anybody question, like, hey, Mr. Dion, Why wouldn't you lose that methyl that you have circled in green? Because then you'd still end up with, if you were to lose that methyl, right? If you had M minus 15 for that methyl, you'd end up with what? You'd have this, 1, 2, 3. You'd have this carbocation, which is a tertiary carbocation. Why don't you do that instead of losing the propyl? You still end up with a tertiary carbocation. This is a tertiary carbocation. The reason why you're going to end up with this in a greater amount is because you can lose M minus 15, but a methyl radical is going to be less stable than a primary radical. Give me a thumbs up if that makes some sense to you. Even if you're like, you know, Mr. Dan, I'm half of the way with you. I'm going to have to look at it on my own personal time, okay? Which is totally normal, okay? Very difficult to come into these lectures and walk out and be like, I understood everything. I know everything there is to know about mass spectrometry. Cool. Okay, there's a couple of other fragmentation patterns. Let me just show you before we do them, because I know you might be a little bit overwhelmed with information, but let me show you. There's a light at the end of the tunnel, okay? The only other fragmentations we learn are with alcohols, amines, and carbonyls, okay? And you can see that 2 of these are on one slide, okay? And then we're basically done, okay? We have one little bit of new content, and that's it. So let me show you what can happen with an alcohol. Alcohols are really common in organic chemistry. So alcohols can undergo 2 types of fragmentation. 2 types of fragmentation. One called alpha cleavage, and the other one called dehydration. You guys know the Greek alphabet, right? I don't, but I know the first little bit of it, right? You have alpha, then you have beta, then you have gamma, then you have delta, right? All you need to know are the first 3 letters, A, B, C. So alpha, beta, gamma, for what we're going to look at here. The carbon that the oxygen of an alcohol is attached to, that's called the alpha carbon. So if you break the bond between the alpha and the beta carbon, I'm never, ever going to ask you to draw this mechanism because that's covered in chapter 10. Don't worry about it. All you need to know is that you're going to break the bond between the alpha and the beta. If that gets broken, you end up with a resonance stabilized cation, not a carbocation, but a cation that's shown here. So it's very common to get what's called this alpha cleavage, okay? Again, it's just a bond broken between the alpha and beta carbon. Again, it's easier to understand when you've tried it or seen it in a problem. Another possibility is that alcohols just lose water. What's the mass of water? 16 plus 2, 18. So if you noticed, all of the fragments that we've lost so far were what? 15, 29, 43, 57. They were all odd numbers. So if you lose 18, that's a dead giveaway that you've lost water and you probably have an alcohol. Amines can also undergo alpha cleavage, the same dang thing you saw with an alcohol. Look, here's the alpha carbon, here's the beta carbon. You break that bond, you get a resonance stabilized cation. Okay, so with amines, oftentimes we see alpha cleavage. Okay, this is what you would detect in the mass spectrometer because it's charged. You would not detect that because it is not charged. Same thing with the alcohol, right? You would detect the cation. You will not detect the radical. It's not charged. And then the last thing is the Mclafferty rearrangement. Look, the Mclafferty rearrangement, I'm not going to go into a whole heck of a lot of detail about the Mclafferty rearrangement. All you need to know is that if you have a carbonyl, and a carbonyl is just a tsatsi show-off name that organic chemists use for ketones and aldehydes, okay? It's just the thing that we say carbonyls, and you're like, come on, Mr. Dion, a carboxylic acid's got a carbonyl. Yeah, I know, but we just use it for aldehydes and ketones. If you have an aldehyde or a ketone, and then you have alpha, beta, gamma, if on the gamma carbon you have a carbon-hydrogen bond, it can undergo this tsatsi rearrangement, like looks really fancy, and you can end up losing a piece here. You can end up losing an alkene. So we'll write it down here, loss of an alkene. And you might be wondering, well, how the heck am I going to know this? Come on, alkene, whoop-de-doo. Here's how you know. It's got an even mass. Okay? So the only times you're going to see even masses lost in this class, okay, read my lips, or if you have a loss of water, because 18 is an even number, or if you have another even number, let's say 30, or 36, or 40, right? Those are even numbers. It means that you've undergone a Mclafferty rearrangement, okay? And that would tell you that you've got either a ketone or an aldehyde, right? So There you go. So here are the common fragments that we're going to use. There are hundreds of different fragments that you could memorize. These are the ones you need to know for our class. This is an introductory course to organic chemistry. You don't need to know everything under the sun, okay? So loss of 15 is a methyl, 29 is an ethyl, 43 is a propyl. And when it says propyl, it could be an isopropyl too. 57 is a butyl. That means it could be a butyl, a tert-butyl, an isobutyl, a sec-butyl. They all count. Loss of 18 is water from an alcohol. That tells you you've got an alcohol. And when you have a loss of an even number that's not 18, you, my friend, have a ketone or an aldehyde, and it's based off of that fancy mechanism called a Mclafferty rearrangement. Okay, the last section that we have to cover is section 14.16. It deals with what's called degrees of unsaturation. I promise you that I can teach you this in under 10 minutes, probably under 5 if I really wanted to go quick, but I don't like doing that. So on Friday, we're going to start with 14.16. I implore you, please take a look at it. All you have to do, you want me to teach it to you in 10 seconds? All you got to know is this formula, okay? And I'll give it to you on your quiz, okay? I'll put it on your handout, okay? So all you got to know how to do is use that formula. Okay, I'll give you a clue. C stands for carbon, N stands for nitrogen, H stands for hydrogen, and X stands for chlorine, fluorine, bromine, or iodine. That's it. And you can figure out how many degrees of unsaturation. Again, we're going to go over it on Friday, okay? So that wasn't me teaching. Just want you to be aware of it. Anyhow, oops. Where am I here? Give me 1 second. Stop recording.